So energetics of solution formation. We can think about the solution forming in 3 steps. The first thing is you've got your solute particles, and let's say it's a solid like sodium chloride. You have to get those particles away from each other, right? So you have to break those intermolecular forces. That's going to require that you put energy in, right? That's going to be an endothermic process. So we'll call that delta H solute. To separate the solute particles, that's going to be greater than 0. Then we also have to separate the solvent particles from each other. Let's say the water. We have to move those particles away from each other, break the hydrogen bonds that are attracting them. That's also going to be endothermic. We have to put energy in. So delta H for the solvent to get separated is greater than 0. When we mix the solute and the solvent, so in my example I just decided to use sodium chloride and water, we're having the water interact with the ions. We've got ion dipole forces. And so that's going to release energy. It's going to be exothermic. As they come together, it releases energy. So delta H, as we mix those two, is less than 0. Well, it releases energy. It's like when you have magnets coming together, right? They just do it by themselves. Because all of these types of attractions really are between opposite electrical charges. So they are very much like magnets. So this is going to release energy, and these two processes require energy to be put in. The overall energy change would be the sum of all of these. Does that make sense? So the enthalpy of solution, the change in energy as a result of forming the solution, is a sum of the changes in enthalpy for each step. The overall sign is going to depend on how large each individual step is, because 2 of them are positive, 1 of them is negative. Whether the sum is positive or negative depends on the sizes of each of those numbers. So solution formation can be exothermic or it can be endothermic. So here looking at 2 different solutions forming. So we're starting here. We've got the solvent aggregated. That means they're together. So the solvent with its intact intermolecular forces, and the solute with its intact intermolecular forces. To separate the solute particles, to pull them away from each other, to prepare them for mixing, requires us to put energy in. To separate the solvent particles from each other, we have to put more energy in. Now we've got solvent and solute particles separated, and then when we mix them, they come together. That's going to release energy. This is not what happens when we form a solution, but it's how we can think of it in terms of what energy changes are happening. So for this one overall, it's an exothermic process. Energy is released. Any questions about that one? Over here, we've got the solvent and the solute, and it requires energy to separate the solute particles. It requires energy to separate the solvent particles. Then when we mix those two together, energy is released. In this case, though, the energy being released is not as great as the sum of the energy that had to be put in. So the overall change is endothermic. Energy must come in. Any questions? A lot of the solutions we use are aqueous solutions, so we're just going to talk about those. Aqueous solutions of ionic compounds. So the heat of solution is equal to the heat of the solute, that's separating the solute particles, plus the heat of the solvent, separating the solvent molecules, the water, plus the heat of mixing. This is going to be positive. Both of these are going to be negative numbers. So what we do is we combine the heat of this solvent being separated with the heat of mixing, and we call this the heat of hydration. that's always going to be a negative number. So that's negative exothermic. This is the energy required to separate the solute particles. That's always positive. And so our heat of solution is going to depend on the relative sizes of these two things. This number here, heat of the solute separating, that is the same value as the lattice energy, just opposite in sign. So this is the lattice energy, but opposite in sign. So if the solution process is exothermic, energy is being released, it's going to feel warm. Some things, when you put like sodium hydroxide solid into water and you mix it, the solution gets warm. It's an exothermic process, the mixing. Other things, you put the solid in the liquid and it becomes cold. It's an endothermic process. It's cold because it's sucking energy in from the surroundings. You can use those sorts of things to make the instant ice packs, cold packs. So if the heat of the solute, which is the lattice energy really, if the energy to putting in to separate is greater than the energy released when the solution forms, then you have an endothermic process. If the solute is greater than the heat of hydration. Stupid pointer. You have an endothermic process. The solution is going to feel cool. If this number is larger than that number, then it's going to be an exothermic process.